Welcome to Lecture 0, Motivating MEMS 1140, Introduction to Programming in Mechanical Engineering. By the end of this lecture video, you will have an understanding of why we as mechanical engineers are even learning programming in the first place, how this course exists to answer that question, how this course will be taught, some example applications for programming in mechanical engineering, and what MEMS 1141 and 1142 after this course will focus on. This slide, the table of contents, links to each section of the lecture so that you can easily navigate the downloaded PDF. And with that, let's address the burning question that may well be plaguing you. I am a mechanical engineer. Why should I learn how to code? Well, the National Academy of Engineering, or the NAE, is a group of experts which provides guidance for the entire field of engineering, and they give a pretty good answer to this question. Let's look at two excerpts from their report, The Engineer of 2020, Visions of Engineering in the New Century, and then think about their messages after. First, regarding the overall engineering profession, we must ask if it serves us well to permit engineering to lag technology and society, especially as technological change occurs at a faster and faster pace. Rather, should the engineering profession anticipate needed advances and prepare for a future where it will provide more benefit to humankind? And second, regarding the tools available to us as engineers, the most important new tool, however, has been the computer. It has allowed us to study very large numbers of examples, millions instead of dozens. Let's pause and take a second to consider what the experts are saying here. First, they give us a question. Is it not our responsibility as engineers to make sure that we stay ahead of the curve of technology? And then they tell us that above all else in this world, the computer is the most important tool for us as engineers. So, according to the experts, it is imperative that we familiarize ourselves with computing. Doing so will make us more effective engineers and therefore equip us to tackle the challenges that face us in the future. And from this call to action, the goal of this course is for you to develop proficiency with programming such that by the end, you will be capable of developing your own scripts to solve real engineering problems. You will have basic programming literacy and be comfortable with things like using the internet to help you while writing code, and you will be prepared for MEMS 1141 and 1142, which will be described more in later slides. This course is designed to focus your attention on real examples within mechanical engineering. This way, everything will be directly relevant to problems that you are already or will soon be familiar with. And most importantly, this course has been designed to ensure that you can focus on learning how to code by giving you problems that you should already know how to solve with pen and paper, and only asking that you solve it with code. This course will utilize the flipped class format, which entails watching short lecture videos such as this one prior to coming to class each week. These videos are designed to be very concise and will require no more than 30 minutes in total. While watching, there may be basic conceptual checkpoints for you to complete to ensure that you are grasping the material. In class, which meets once per week for 50 minutes, will be entirely programming practice. The exercises will apply the concepts from the lecture videos to solve real problems. And with that, I'd like to showcase a couple of example projects that utilize coding in other mechanical engineering classes. These are projects that could not be feasibly done by hand because they require many repetitions. The point here is to highlight that coding is more than just writing code. It's a tool that enables you as an engineer to do more robust and complex analyses of real and relevant systems. First up, we have the Bridge project from Engineering 135 or Statics 1. If you are not already familiar, the goal of this project is to design optimize, and construct a balsa wood bridge. Here you can see a truss from students in the past, and on the left you can see where it actually broke. The first step of this project is to design the bridge and solve for all of its forces. You could feasibly do that a single time and then move on to constructing it, but recall part of the objective is to optimize the design. With pen and paper, perhaps you could be doing that 2 or 3 times, but what about 100 or 1000? That's where code becomes your best friend. Here's what that process looks like. With just a little bit of code, you can have the computer do all of the math for you. And because the computer stores everything, you can even turn that into some really great visualizations like this image, which highlights the load that each part of the bridge is experiencing. This picture gives you a sense of how the bridge will behave during testing without the need to even build anything. Then the optimization step is pretty straightforward too. It's very easy to repeatedly test many variations of the bridge to find the best one, and here we can see the performance index, or the PI, plotted against an angle theta. The best bridge design is found at the maximum of the PI, which is right around 70 degrees. And once that process is complete and you have done a thorough optimization study, you can build the real bridge and be confident that your bridge is the best that it can be. For this project, programming is used as an optimization tool, but in this next one, it's used for even more than that. Here we'll look at a project from MEMS 1120, which is a simulations class. In this design of a 3D printed toothpick crossbow, the thin ribs connecting the central pin to the outer casing serve as springs. The goal of the project here is to vary the number and size of those ribs and to find which configuration stores the most elastic energy. The first step in this project is to generate the 3D models for each variation. So these students wrote a script that automates SOLIDWORKS to produce all the models in just a few seconds without any user input. Creating the same high number of models manually would take hours. Once each model is generated, they can all be tested by automating ANSYS, which is a very powerful simulation tool. And again, doing this step manually would add hours of work, but code all but eliminates that time. And then just like with the bridge, there's an opportunity for visualization of your data. Here they plot the spring stiffness for every variation to illuminate a trend. And finally, with the optimized design, they can 3D print the best configuration. This project is more advanced than the bridge project because it requires relatively deep familiarity with both SOLIDWORKS and ANSYS, but it is crystal clear that even CAD and simulation, which were designed to be used in a manual and interactive way, can benefit hugely from applying programming as an additional tool. And even beyond these two example projects, much of the mechanical engineering curriculum utilizes programming in some manner. For the sake of not droning on, I won't read this list, but the courses marked here with an asterisk require the use of MATLAB, and those marked with a dagger are required in the mechanical engineering curriculum in general. And finally, MEMS 1140 doesn't exist in isolation. MEMS 1141 and 1142 are two follow-up courses which introduce the foundations of linear and nonlinear regression and machine learning for mechanical engineering problems. The goal of these two courses is to develop proficiency with data-driven modeling in engineering, such that you are prepared to be an engineer in a world of high-capacity computing and AI. To end, let's quickly recap what was covered in this video. The NAE emphasizes that learning how to code is essential for engineers to remain competent in an ever-changing technological landscape. And MEMS 1140 is designed to incorporate programming into the mechanical engineering curriculum at Pitt such that our students are prepared to meet those expectations. Then we covered how this course will be structured to effectively meet that goal with its flipped format and in-person practice, and we highlighted some examples of how programming can be used to enhance mechanical engineering projects. And finally, we introduced MEMS 1141 and 1142 as the two follow-up courses to this one.